Hey, once again, welcome everybody to the AMATIC 2020 webinar series. Today we have Alan Rossman on teaching introductory statistics, asking good questions. The views expressed by the presenter are not necessarily the views of AMATIC. Commercial products mentioned by the presenter is not endorsed by AMATIC. McGraw-Hill, thank you for your sponsoring of the 2020 AMATIC webinar series. Okay, so Alan, I will stop sharing here. And while he's getting his slides up, let me introduce Alan Rossman as Professor of Statistics at Cal Poly San Luis Obispo. He has taught statistics primarily at the introductory level for undergraduates for 30 years. He has served on committees that develop GAISE recommendations and is a member of the ASA AMATIC committee. He's received teaching awards from ASA and MAA. He writes a weekly blog about teaching introductory statistics at askgoodquestions.blog. So welcome, Alan, and I will turn it over to you.
Thanks very much, Pat. Can you see my slides now?
You're good.
Good to go. Thank you, Pat. Thanks to Julie Hansen, who's the chair of the AMATIC Statistics Committee, who helped with a lot of putting this webinar together. And thanks especially to all of you who are here to listen to what I have to say for the next 45 minutes here. As Pat mentioned, my title is Teaching Introductory Statistics, Ask Good Questions. I suspect that all AMATIC webinars start with a picture of Frank Sinatra, and mine will be no exception there. So what in the world does Frank Sinatra have to do with teaching statistics? Well, legend has it that Frank Sinatra was once asked, what's the secret to being a successful singer? And legend has it that his answer was, sing good songs. Well, a few years ago, I was asked to give a talk, and I took my charge to be, what's the secret to being an effective teacher of statistics? And it occurred to me that I had a similarly succinct suggestion. And that suggestion is what you already know from the title, ask good questions. But that's my take-home message. At the end of the talk, I'm going to give you a quiz. I'm going to ask what the take-home message was. I'll tell you right now, the answer is ask good questions. That's what I hope to impress upon you today. What kind of questions? What purposes of questions? Well, I'm going to talk about two kinds of questions. One is questions that guide students to develop their understanding and skills. You can think of those as formative assessment questions or learning activities. The other type of question is the conventional question that assesses what students have learned. You can think of those as summative assessment questions or quiz or exam questions. The presentation today will be giving you examples of what I think are good questions for helping students learn statistics. What topics will I address with these questions? We'll run pretty much the gamut of a typical introductory statistics course. I've got a few at the beginning on what I'll call statistical thinking, and then several on basic descriptive statistics, a few on sampling and experimentation. I have just one today on probability, and then several on statistical inference, both simulation-based inference and more conventional inference techniques with confidence intervals and hypothesis tests. So that's my plan. I hope that's what you thought you were signing up for. Let's jump right in. First two examples are about statistical thinking. And I use these on day one of a statistical literacy course that I teach here at Cal Poly. Both of these are somewhat well-known examples. There's nothing original in the examples. You may have seen one or both of these examples before. The first one is from the 1970s, when UC Berkeley was concerned about possibly being sued for discriminating against women in their graduate admissions policies. So here's some data. There's a 2x2 table of counts. You can see the number of men accepted into the programs we're looking at and the number of men denied admission. The number of women accepted, the number of women denied admission. So if you were in students in a real class of mine, I would start by saying, what do we do? What's the first thing we should do with these data? And if I don't get a response, I might say, do we just compare the 533 and the 113? Is that what we should look at? And at that point, someone says, no, we need to look at proportions. We've got different numbers of men and women who applied, so we need to calculate proportions who were accepted for each gender. And again, if you were in my class in a real setting, I'd ask you to get your calculators out or even your cell phones out to use as calculators and calculate these proportions. But we can make better use of our time here today by me telling you what these proportions are. There you go. Does that seem like a big difference? It sure seems like a big difference. It's no wonder that lawyers got excited at the potential here that men had a considerably higher acceptance rate than women. So what's going on here? Does this provide evidence of discrimination against women? Well, let's dig a little deeper. Let's look at a third variable here. Let's look at the program that they applied to, because decisions at the graduate level are made not at the university, but program by program. So let's take these data, these counts, and classify them according to program. So there's the same data from the previous slide, but now classified by program as well. I'll call these programs A and F. And if you remember the counts from the previous slide, they're the same here. 533 men accepted, 665 men denied, and so on. So I'm not cheating or anything. It's the same data. It's broken down by one more level of classification. What do we do next? Well, students are quick to tell me we need to calculate more proportions within each program. Find the proportion of men who were accepted and the proportion of women who were accepted. So it takes students a few minutes to do that, or a minute or two to do that. I'll save you the bother. Program A, there's the proportions. Program F, there's the proportions. Something weird is going on here. Many students realize that for themselves. If not, I tell them something weird is going on here. What's the oddity? Well, the oddity is men had a much higher proportion of acceptance overall, and yet within each program, men have a smaller proportion of acceptance than women. It's a small difference in program F. It's a pretty big difference in program A. So my next question to students is describe the oddity, which I just did. The harder question, the important question is explain the oddity. Use the data given to explain what's going on here. How would you explain this to a university official? How would you explain it to a potential applicant? How would you explain it to a judge or jury if it got to that point? And this is somewhat challenging, of course. You really have to think this through, but students can handle it with perhaps a nudge in the right direction. If they need a nudge, I'll say something like, where did most of the men apply? Where did most of the women apply? And they're quick to tell me men applied in huge numbers to program A. 800 and some men applied to A. 300 and some men applied to F. So more than twice as many men applied to A as F. How about women? Well, women applied mostly to F. 3 times as many women applied to F as applied to A. So that's a good start, but that doesn't fully explain the oddity. If they need a nudge, I'll say, what else is different between A and F? And students are then pretty quick to point out, A is pretty easy to get in. A has acceptance rates higher than 60% for both genders. F has acceptance rate below 10% for both genders. A is pretty easy to get in. F is pretty hard to get in. If you combine that with the previous observation, men apply mostly to A, women apply mostly to F, that explains the oddity. We can explain that in one sentence by saying, men apply mostly to the easy program to get in, women apply mostly to the hard program to get in. That's why men have a higher acceptance rate overall, but a lower acceptance rate in each category, in each program. And I claim that's an example of statistical thinking. You could call it multivariable thinking. There's 3 variables at play there. The gender of the applicant's a variable, the decision on admission is a variable, and the program is a 3rd variable. What we're illustrating here is sometimes known as Simpson's paradox. I don't necessarily throw that term at students on day 1, but I do want them to be able to think these things through. I usually say something like, did we do really sophisticated mathematics there? No, we calculated proportions, we added and we divided. That's all the math we did. And yet there's some fairly sophisticated statistical thinking going on there. Second example of statistical thinking, another one I use on day 1 of class in a statistical literacy class. Another one that's based on real data from the 1970s. This is probably an even more famous example. I suspect lots of you have seen these data before. It's the 1970 draft lottery. And of course, students don't know what was happening in the world in 1970 to any great extent. So I start by explaining that in 1970, the Vietnam War was going on, and the US decided they needed to institute a draft system to induct young men into the military. There weren't enough volunteers, so they needed to draft some young men into the military. And of course, that's a huge, 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 huge deal. I'm old enough, I was alive then, but I'm not so old that I remember the actual draft lottery. I tell students, but it was a huge, huge, huge deal, as you can imagine. And they had a pretty clever and good idea, I think. They decided to base the lottery on birthdays. And I think that was a very good idea. There's nothing about birthdays that would advantage one ethnic group over another, one financial group over another. It doesn't matter whether you're rich or poor, what birthday you have. So they decided that each birthday of the year would be assigned a draft number. If you were born on the date that got draft number 1, you were in the very first group to be drafted. And draft number 2, and so on, up through number 366, including February 29th. So what are we looking at here? Here's a graph, a scatter plot of number, the day number of the year on the x-axis. So that simply means January 1st is day 1, January 2nd is day 2, and so on through December 31st is day 366. On the y-axis is the draft number assigned to that date. How was the lottery done? Well, they essentially had a big bin with 366 ping pong balls. Inside each ping pong ball was a slip of paper with a date written on it. They mixed them up and they pulled them out. First date that came out was September 14th. So September 14th got draft number 1. So anyway, that's a lot of background of the draft lottery. The first question is, what do you see in that graph? Is there any reason to doubt that this was a fair random lottery process? And pretty much everyone, when they first look at this graph, says, it sure looks like random scatter. There's nothing suspicious here. Should it look like random scatter? Sure, if it's a fair random lottery, there shouldn't be any pattern in this graph. So that's what students pretty much always say. And then again, I ask them to dig a little bit deeper. I give them the actual draft numbers and arranged by month. And I ask them to calculate the median draft number for each month. Actually, I asked them to do the median draft number for their birth month, and then we combine the results with the rest of the class. Of course, they need to realize to calculate a median, you first need to put the draft numbers in order within each month. And that would take an awfully long time to do by hand, so I give them the ordered list for each month as well. And then it's pretty straightforward to calculate the medians. I'll save a lot of time again by showing you the medians. There they are. And the next question is, do you see anything here? Do you see any pattern? Do you see any trend? And students do see a trend there. They point out that in the first half of the year, every single median in the first 6 months is bigger than every single median in the second 6 months. And that seems pretty surprising. If we go back and look at the scatter plot now, I'm going to superimpose those medians at the appropriate points on the scatter plot. So with those medians superimposed there, you can see a bit of a downward trend, a bit of a decreasing trend as the year goes along. There's a bit of a tendency, it seems, for earlier birthdays to have higher draft numbers, or later in the year birthdays to have lower draft numbers. So even though we couldn't see anything in the original graph because of all that noise, something as simple as calculating medians allows us to see perhaps a bit of a signal there. We could take this one step further. We could say, well, how often would you get such an extreme outcome with a truly random lottery? Well, to investigate that, we need to decide how are we going to measure extremeness. A natural choice here is with the correlation coefficient. We can calculate the correlation coefficient between day number of the year and draft number assigned to that birthday. It turns out the correlation here is negative 0.226, which is pretty small, but it's not zero. How often would you get a correlation coefficient as far away from zero as negative 0.226 in a truly fair random lottery? Well, here's where computers are really helpful. We can program a computer to perform a random lottery and to do it many, many, many times. And to calculate the correlation coefficient between day number and draft number every time. Let me show you the result. There's the result of simulating draft lotteries 10,000 times, looking at the value of the correlation coefficient between day number and draft number for each of those 10,000 random lotteries. What are you supposed to see there? You might see sort of a bell-shaped curve. You might see it centered at zero. What we really care about here is the question, how extreme is negative 0.226? And the answer is it's way, way out there. In these 10,000 repetitions, we never got a correlation as far from zero as negative 0.226. So we actually have very strong evidence that the 1970 draft lottery was not a truly fair random lottery. The explanation is they didn't mix the balls very well. They put the January balls in first and then February and so on. By the time they got to November and December, they did not get mixed very thoroughly, which turned out to be an advantage to people born earlier in the year, tending to get higher draft. So anyway, the first part of this example with the medians didn't involve much math at all, and yet I think we were doing statistical thinking. The second part with essentially simulating a randomization test, I saved that for later in the course. Those are two examples of learning activities that one can introduce largely on day one of the course, give students a sense for what statistical thinking is, and to point out you don't need to use sophisticated mathematics to do serious statistical thinking, and to point out you can investigate important issues for society with statistical thinking. Discrimination, the draft lottery was awfully important at the time as well. Let me talk about descriptive statistics for the next several questions, and these are going to come pretty quickly because they deal with pretty basic things. First off, here's a joke I like to tell in class. I suspect that when I moved from Pennsylvania to California 19 years ago now, I suspect the average IQ dropped in both states. Apologies to anyone in Pennsylvania listening to this webinar. What's the question for students? Well, is this possible in principle? And what would have to be true for this to happen? Well, I contend that asking this question can help students think through how averages work. I think a question like this is more valuable than giving students 10 numbers and asking them to calculate the average. And students are pretty quick to point out, sure, this is possible. What would have to happen? Well, if the average IQ in Pennsylvania dropped when I left, that means I was above average in Pennsylvania. And clearly students realize I'm below average in California, so when I entered California, the average IQ dropped in California. So if those two things are true, this joke could actually happen. Let's change from measures of center to measures of variability. Let's talk about standard deviation in this next example. Suppose two students record ages of customers, one at the on-campus snack bar, which is called the Avenue here at Cal Poly. Let's say Abby goes to the Avenue. Let's say Mary goes to the McDonald's near the freeway. And they keep track of the ages of customers for several hours at lunchtime today. The question for students is, who's going to have the larger standard deviation of customer ages, Abby or Mary? What do you need to know? You need to know standard deviation is a measure of variability. The larger the variability in ages, the larger the standard deviation. You also have to have some sense that at McDonald's, you get all ages from infants to senior citizens. On campus, you get mostly 18 to 25-year-olds. But some older people, perhaps some younger people. But there's going to be more variability of ages at McDonald's than in the campus food line. So Mary is going to have the larger standard deviation of ages. And again, I think a question like this gets at whether students understand the concept of variability and the idea of standard deviation as a measure of variability, as opposed to giving them a bunch of numbers and asking them to calculate a standard deviation. This next one is a similar point. Here's hypothetical data on ratings of 4 restaurants. And I asked students to put these 4 restaurants in order from the largest to smallest standard deviation of the rating. And this is non-trivial for students. But again, it comes back to understanding standard deviation as a measure of variability. The least variability here is restaurant B. Everyone agreed on restaurant B. So B has the smallest standard deviation. The largest standard deviation is restaurant C. People are very torn on restaurant C. Half think it's lousy, half think it's great. A and D are in between. Between A and D, A has the smaller standard deviation because A has more concentration near the middle. D is more evenly spread out than B. Here's an example that I like a lot. I got the first half of this example from Jay Lehman, who teaches at the College of San Mateo. One of the reasons I like the example is I really like cats and the examples about cats. And I was happy when I gave this question to my students. My students did just fine on this question. They realized that people weigh more than cats in general. So the mean weight of 10 randomly selected people is going to be larger than the mean weight of 1,000 randomly selected cats. Perhaps you might be tempted to think 1,000 of anything is going to be bigger than 10 of anything. That's what a mean, that's what an average is all about making it on a per unit basis. So the mean weight of people is going to be bigger than the mean weight of cats, no matter how many people or how many cats. As I say, my students did fine with that. My students did not do fine with part B. Part B is essentially the same question, now asking about the standard deviation of the weights. And I said, suppose it's 1,000 people and 10 cats. Standard deviation is a measure of variability. Who has weights that vary more, people or cats? The answer is people. People's weights vary from very little in infants to hundreds of pounds. Cats' weights vary from very little in kittens to maybe a few dozen pounds in really, really large cats. So human beings have a lot more variability in weights than cats do. The correct answer is people. Why do lots of my students pick cats? I think it's because of the sample sizes. I think that many of my students think they've learned that a larger sample size means a smaller standard deviation. They probably think I said that in class. I promise you I never said that in class. What I said was a larger sample size produces a smaller standard deviation of a sample mean or of a sample proportion or of some sample statistic like that. But here we're talking about the standard deviation of the weights, not about a sample mean weight or sample anything, but of the weights themselves. So my students don't do well with question B, I'm sorry to say, but I think that has shown me something important that I need to emphasize to my students. My advice to myself, and I'll offer it to you, is anytime I talk about standard deviation, I try to always remember to say standard deviation of what? Make clear what it is I'm talking about, the standard deviation. Another descriptive statistics example. Suppose a set of exam scores have a mean of 70, a standard deviation of 8. Suppose Arturo's score is 75, Bella's score is 1.5 standard deviations above Arturo's. The question is simply, what's Bella's score? I just started asking this question recently. I mean, for my whole teaching career, I've wanted students to understand that z-scores tell you how many standard deviations away from the mean the observation of interest is. So that idea of measuring distance by number of standard deviations away is, I think, an important idea. It occurred to me if all I ever do is ask students to interpret a z-score, I haven't really gotten at, do they understand the idea of measuring distance by number of standard deviations away? Here I asked them about number of standard deviations from a different person's score, not from the mean. And it's a straightforward calculation, of course, but you have to have some understanding of the concept of measuring distance by number of standard deviations away. A couple more, at least one more on descriptive statistics. Suppose every student in our class scores 5 points lower on the second exam than on the first exam. The question is, what would be the value of the correlation coefficient between exam 1 score and exam 2 score? And I used to offer this as a free response question. Lately, I've made it multiple choice with these options. And of course, I get very discouraged when a student picks -5 as the answer, since correlation coefficient has to be between -1 and +1. I think the most common answer I get is -1. But that's not correct. Why? Because think about what the scatter plot would look like. Students who score on the low end on exam 1, they're also on the low end of exam 2. Students on the high end of exam 1, they're at the high end of exam 2. It's a positive correlation. In fact, it's as positive as you can get. The scatter plot would show a perfect straight line with a positive slope. So the correct answer here is a correlation of positive. This slide doesn't really fit in, but I wanted to show it somewhere, so I stuck it in here just to show you the degree to which undergraduate statistics enrollments have been increasing over the last 15 or 20 years. This is from the CBMS survey. 2015 is the most recent one. The survey is conducted every 5 years, so one will be coming up this coming fall. These are in thousands. The number of students taking statistics courses in the US in thousands, in four-year college math departments on the left, statistics departments in the middle, and two-year college math programs on the right. And the numbers are increasing dramatically in all three groups. They're increasing most dramatically in two-year colleges. This number is essentially quadrupled in the last 15 years in two-year colleges. And I suspect it's going to be a pretty substantial increase from 2015 to 2020 as well. You'll notice more students in the US study introductory statistics in two-year college math programs than in four-year college math programs. That was a bit of an aside there. Let's go back to questions for teaching introductory statistics. The next topic is sampling and experimentation. Let's talk about the Gettysburg Address. You didn't expect to see Frank Sinatra. You probably didn't expect to see the Gettysburg Address here today. I'm not going to actually show you the address. I do show it to students. What I ask them to do is take a sample of 10 words from that population of 268. And they often give me a blank stare at first, and I say, just circle 10 words. Don't give it much thought. Just circle 10 words on the page that's in front of them. And then what do I ask them to do with those 10 words? I ask them to record the length, the number of letters in each word, calculate the average length for their sample of 10 words, and then come up to the board and put their sample average as a dot on the dot plot that we produce on the board with all the students in the class. The question then is this a reasonable sampling method for estimating the average word length in the population? And you know the answer, I suspect. Let me show you some representative results from a class of mine. There's the dots that students put on the board in a recent class. Why is the vertical line there? The vertical line is at the population mean. The true population average is 4.295. And you can see the big majority of my students had a sample mean that was larger than the population mean. And I think that illustrates the concept of sampling bias. What is it about that graph that indicates sampling bias? It's not the shape. It's not the variability. It's the fact that a big majority of the sample means are larger than the population mean. That indicates there's a systematic tendency of this sampling method to produce words that are bigger than typical in the population. I'm quick to tell students it's not their fault. I say sampling bias is a property of the method. Whose idea was this method? It was my idea. I'm the one that told them to circle 10 words. And so I hope they understand that it's my fault here. Of course, I did this on purpose to illustrate what sampling bias means. And then I say something like, give me a chance, give me a second chance. Let me come up with a new method. I say, well, what could be more unbiased than closing your eyes? Close your eyes and point at the page 10 times. Would that be unbiased? And students are pretty quick to realize that would not solve this problem. The larger words take up more room on the page. If you close your eyes and point, you're more likely to hit a large word than a small word. So we're going to still have bias toward larger word. So that's an activity. That activity takes probably half an hour of class time that I just hurried through in 2 minutes of our webinar time. Let's talk about experimentation. Here's a quick description of an activity I do that has to do with guessing Nelson Mandela's age when he died. So I give half the students in the room a slip of paper with these two questions on it. I'll give you a chance to read the questions. I do tell them who Nelson Mandela was in case anyone doesn't know. You can see the first question there is ridiculous. Of course, Mandela was older than 16 years old when he died. That's not a relevant question at all. Why am I bothering to ask that? Well, this is group one. I may or may not have mentioned a moment ago, I give two different versions of this question. Half the class gets version 1, the other half gets version 2. Look closely to find the difference in version 2. There's only one character difference in version 2. The difference is, I'm asking about 160 years old instead of 16. That's a ridiculous number to ask about. Of course, Mandela was less than 160 years old when he died. So the point here is the first question is not a relevant question at all. What I'm doing here is an honest-to-goodness randomized experiment. I've randomly assigned students to either version A or version B. The response variable we're focusing on is the student's guess for how old Mandela was when he died. The explanatory variable is the number given in the first question. We could call that the anchor number, because what we're investigating here is the psychological phenomenon known as anchoring, which suggests that just seeing that number 16 or just seeing that number 160 could psychologically, subconsciously affect people's responses to the more relevant question coming next. So let me show you some data from a recent class. There's the results. And sure enough, you can see there is a tendency for the students who saw the 160 number to give bigger age guesses on average than students who saw the 16. If you do a t-test, it's highly, highly significant. The p-value is 0 to several places. So there's very strong evidence here for an anchoring effect. The point is not that students study the phenomenon of anchoring. The point is to introduce random assignment and the benefits of random assignment and what that buys you in terms of the scope of conclusions you can draw. When I started my teaching 30 years ago, to be honest, I don't think I made a big deal of random sampling versus random assignment. I've come to realize those are extremely different things, different tools with very different purposes. And I think it's a big deal to help introductory students understand those differences. Random sampling is about trying to get a representative sample from a population. The benefit is you can then generalize findings from your sample to the larger population. Random assignment is not about that at all. Random assignment is about trying to produce similar groups before the explanatory variable is imposed, with the benefit that if you then see a significant difference between the groups, you have the potential to draw cause and effect conclusion. Sorry. One thing that I've come to do in my classes all the time is ask some questions over and over and over again. Virtually every example I use in the course, students get sick of hearing these questions, I'm sure, but I think it's important to ask them over and over again. And those questions are, what are the observational units? What are the variables? What type of variable is it? Which is explanatory, which is response? Did the study make use of random sampling, random assignment, both, neither? Is it an observational study or an experiment? After we've introduced those ideas in the first couple of weeks of class, my students hear these questions virtually every example, so several times a day for the rest of the class. But as I say, I think those questions are crucial to understand what to do with the data and what kind of conclusion you can draw from the data. I mentioned at the outset, I only have one probability question. Here it is. Here's real data from the 2018 General Social Survey, which found that 47% of American households surveyed said they have a pet dog, 25% have a pet cat. The question I asked students is, does this mean 72% have a pet dog or a pet cat? And of course, the answer is no. Why not? Because some households have both. This would only be true if no households have both dogs and cats. So only so much time today. Of course, I'm not going to show more probability questions. Let's move on to statistical inference. And we'll start with simulation-based inference. And we'll start with a real study. There's two faces. I read about these faces. I saw these faces in a psychology journal article several years ago now about a phenomenon called facial prototyping, which is the idea that people tend to associate certain names with certain facial characteristics and vice versa. So I collect data from the students. I show them these two faces. I tell them one of them's Bob, one of them's Tim. Who do you think's on the left? And I only give them 10 or so seconds to think about it. And then we do a show of hands. It turns out that Tim is on the left. And it turns out in almost all of my classes that 70 to 80% of students associate Tim with the face on the left. In a recent class, 36 out of 46 put Tim on the left. Oh. So what do we do with that? Well, I asked students, what are some explanations for that result? And that's a tough question. I have to do a little bit more guiding to get them to go where I want them to go with that question. But eventually what I'm looking for is, well, one explanation is facial prototyping is real. People do tend to associate the name Tim with the face on the left. Another possible explanation, which is a tough one for people to think about, is that it could just be random chance. Maybe there's nothing to this facial prototyping theory. People are mentally flipping a coin to decide whether to say Tim's on the left or Bob's on the left. And then I say something like, well, which of those explanations can we investigate? Which of those explanations can we model? And they say, well, the random chance explanation, because we could use literal coin flips to investigate that model. I have students flip a coin, an actual coin, 46 times. Of course, I have to take coins to class because students don't carry coins. But they flip a coin 46 times. They count the number of heads. Head represents putting Tim on the left. Tails represents putting Bob on the left. So they count the number of heads. They come up to the board. They put a dot on the board for the number of heads. What's the point? I usually joke that took 5 minutes, but what was the point? Now, the point is to see how unusual, how surprising would it be to get such a majority putting Tim on the left if there were no facial prototyping, if it was just mental coin flips. So let me show you some results, not from students flipping coins, but from an applet. So this is using an applet to generate 10,000 simulated samples of 46 students, assuming that it's just a coin flip to decide whether it's Bob or Tim on the left. And you can see we never, in 10,000 repetitions, we never got 36 or more heads out of 46,000. It's not impossible, it's just extremely unlikely. And so we have very strong evidence against the random chance explanation in favor of the facial prototyping explanation. So again, that's a 30-minute class activity that I've rushed through in 2 minutes with you today. But that's an idea for how to ask a series of questions, introduce students to the ideas of statistical inference, and you could even use the term p-value here if you want to introduce that term. And my colleagues and I contend you can do this very early in the course. You could do this activity in week 1 if you want to introduce these ideas early on. Let's talk about confidence intervals for a couple of minutes. What does 95% confidence mean? To be honest, that's a pretty hard question. To be really honest, I think sometimes I overemphasize this point in class. I think statistics teachers in general tend to put too much stock in having students understand what 95% confidence means. Let me give you an idea for how to help students understand what that means. But what does it mean? It means if you repeated the procedure over and over again, then 95% of the intervals generated by the procedure would succeed in their goal of capturing the population parameter they're trying to estimate if you applied the procedure over and over and over again in the long run. That's a hard idea. Anytime you get into a concept that involves applying a procedure over and over and looking at the percent that succeed in the long run, there's a lot there. You won't be surprised, I don't think, to hear me say, I think an effective way to help students understand that is to visualize it through simulation. By having a computer select random samples over and over again and generating the confidence interval and seeing yes or no, does the confidence interval succeed in capturing the population parameter it's trying to estimate. So there's the result of simulating this confidence interval procedure 100 times. This happens to be a confidence interval for a population proportion. I designated the value of the population proportion to be 0.4. That's the vertical black line. And these horizontal lines, segments, are the confidence intervals. The black dots in the middle of these line segments are the midpoints of the intervals, which of course are the sample proportion of successes in each of those 100 samples. The color coding is not hard to guess. Green means an interval that succeeded in capturing the population proportion value. Red indicates an interval that did not succeed. And you can see out of these 100 intervals, 95 of them are green, only 5 of them are red. If we arrange these in order, we can see even more clearly the red ones are the ones that had an unlucky large value of the sample proportion or an unlucky small value of the sample proportion. And I don't just present these to students as I'm presenting them to you. Students are playing around with the applet in class. What do I mean play around? You can ask them what will change if we increase or decrease the confidence level. We go from 95% to 80%. If we go up to 99%, what two things are going to change. And students are pretty good at guessing. Well, the width is going to change, and the proportion of green versus red is going to change. On the left, we've got 99% intervals, which are wider and which have a lot higher percentage succeeding. On the right, we've got 80% confidence intervals, which are narrower, that's good, but have a lot more intervals that fail to capture the population value. That's bad. You can also change the sample size. Students are pretty quick to realize with a smaller sample size, you get a wider interval. But many of them predict that a larger sample size will do better at capturing the population value. We'll have a higher percentage that capture the population value. But of course, if you don't change the confidence level, it's still going to be about 95% succeeding regardless of sample size. Here's one of my favorite questions. It's ridiculous. Bear with me, please. Suppose an alien lands on Earth, wants to estimate the proportion of humans that are female. The alien had a good statistics course on its home planet, so it knows it should take a sample and produce a confidence interval. Let's suppose the alien happens upon the US Senate as its sample of human beings. The current Senate has 26 women, the most ever. In fact, a new woman senator was sworn in a couple of weeks ago. And so the alien is going to have 26% women in its sample. And it can do the calculation to calculate the confidence interval. There it is. And it can interpret that by saying 95% confident that between 17.4% and 34.6% of all humans are female. And I do actually have students do that calculation by hand and write the interpretation by hand. I think it's good practice to do that. But the key question, the important question, the reason to go into this silly example is this one. Is that interval consistent with your experience as a long-term resident of this planet? Of course not. The alien's interval has failed horribly here. So I ask, does this go back to the point that 5% of all 95% confidence intervals fail? Students are tempted to say yes. I don't blame them for saying yes, but that's not the right answer here. That's not the problem. 5% of all intervals fail if you've done everything right, if all the conditions are satisfied. The problem here is the sampling method is horribly biased. Last question on this example, and this is a challenging one for students. If the alien was only interested in estimating the proportion of current senators who are female, would this interval make sense? Would you say you're 95% confident that between 17 and 35% of current senators are female? No, that's ridiculous too. If you only want to know about current senators, 26 out of 100 are female, it's 26%, period, end of story. There's no inference to be done if the data you have comprise the entire population. Here's an example that talks about both intervals and tests. It deals with cats. That's one of the reasons I like this example. Survey of 47,000 households a while ago found that 32.4% had a cat. Here's the two questions I asked students. Does this provide very strong evidence that the population proportion with a cat is different from a third? Does this provide strong evidence that the population proportion with a cat is very different from a third? But boy, those sound similar. They are very, very similar. The difference is very strong evidence versus very different. The point I want students to see here is when you're asking about strength of evidence, that's answered with a hypothesis test with a p-value. When you're asking about how different, that is best answered with an interval estimate with a confidence interval. So let me show you the p-value. It's virtually 0. The z-statistic is bigger than 4 in absolute value. Confidence interval goes from 0.317 to 0.331. And that's a 99.9% interval. Why so confident? Because cats are so important. We have to be awfully confident when we're doing it. That was a joke. Are these consistent? Yes, they're consistent. The test said we reject the value 1/3. The interval does not include the value 1/3. The test and the interval are consistent. But notice that the whole point here is statistical significance is very different from practical importance. And that's an especially relevant consideration with large sample size, such as 47,000 households. Just for the fun of it, there's my cats. Eponine on the left, Cosette on top, Hootie on the bottom. Eponine and Cosette are no longer with us. That's Prudy on the bottom. He's a very good boy, and I'll see him at home this evening. None of that will be on the quiz. There won't even be a quiz. I've got a few minutes left, and then we'll have some time for questions. I do want to talk about my blog. Pat mentioned my blog when he introduced me. Thanks for that, Pat. I'm actually on leave from Cal Poly this year on a sabbatical like leave. And my primary project is to write a weekly blog about teaching statistics. As you know, my teaching philosophy is just 3 words: ask good questions. So the name of the blog is Ask Good Questions. The blog contains ideas, examples, activities, assessments, and advice for teaching introductory statistics. I have 2 goals with each blog post. One is I want each post to be very practical, something you can use directly with students. Makes me very happy when someone emails me and says, I read your blog post on Monday. I used some of those questions with my students on Wednesday. The other thing I try to achieve is I want them to be thought-provoking. I hope that the faculty will get together and have conversations with their peers about what to teach them and how to teach statistics based on what I present in my blog. I think I mentioned there's 1 blog post per week. Sometimes I call them essays instead of posts because these are not single paragraphs. These are 2,000 to 3,000 words per essay. I publish them every Monday morning, 11 a.m. Eastern Time, 8 a.m. Pacific Time. I started back in July, and there have been 28 posted so far, with at least 24 more to come. I pledged to myself to write 1 essay per week for a year. We'll see if I run out of ideas or if I run out of time or if I decide to continue past that. Let me give you an example. Let me show you the highlights of this week's blog post from 2 days ago. I present data from the Youth Risky Behavior Surveillance Survey, comparing Arizona youth with California youth. The question here was, how often do you wear a seatbelt when you're riding with someone else driving? And the options were rarely, never, sometimes, most of the time, or always. We're classifying rarely and never together. It turns out about 8% of Arizona teenagers said rarely or never, but less than 6% of California teenagers did. So let's take the difference between those 2 proportions. We get 0.023. Here's the key question that this week's blog post hinges on. Does that mean Arizona kids are 2.3% more likely to respond rarely or never than California kids? And that's tempting to say that. Most students think that sounds just fine. Most people, I think that sounds just fine. But that's not true. That's not what a percentage difference is about. We can say the difference between Arizona and California is 2.3 percentage points, but that's a different statement than talking about percentage difference. I know this isn't the biggest idea in introductory statistics. It's not that big a deal. That's why I titled the post a pervasive pet peeve. This is just a pet peeve of mine. Let's go back and calculate the honest to goodness percentage difference. How do we do that? We take the actual difference and divide by whichever group we want to treat as the baseline group or the reference group. Let's use California as the reference group. So it turns out that Arizona kids are 39.6% more likely to respond rarely or never compared to California kids. I also sneak in a statistic we typically don't teach in a Stat 101 course. Let's take, instead of the difference between those proportions, let's take the ratio. That ratio is sometimes called the relative risk. And my point is not that we should be teaching relative risk in intro stat. My point is we could just as well take the ratio of those proportions as the difference. When we do that, we get 1.396. Does that look familiar? Sure, that looks familiar. Well, first, we can interpret that. Arizona kids were 1.396 times more likely to respond rarely or never than California kids. Why times more likely? Because we took a ratio. There's where the times is coming from. But notice that gives you the 39.6% more likely. There's a clear connection between relative risk and percentage difference. And again, I'm not arguing we need to teach relative risk. I am arguing most students get confused about percentage difference. We could take the opportunity to help them understand that in an introductory statistics. So I thought about titling this week's post a persnickety post that preaches about a pervasive, persistent, and pernicious pet peeve concerning percentages. I try to be cute and funny in my posts. It's up to readers to decide whether I succeed or not, but there's an attempt. Turns out that 60% of the words in that potential title begin with P. In the actual title I used, a pervasive pet peeve, 75% of the words begin with P. So does that mean that by changing titles, I had a 15% increase in the percentage of P words? No, that's the whole point. That's my pet peeve. So that's an example of me trying to be cute and amusing, and you can decide whether I succeed to any degree there. But that's what the posts try to do, not be cute and amusing, although there's some attempt at that, but to try to be thought-provoking about what and how to teach, and even more importantly, to give examples that you can use directly with your students, all based on the premise of asking good questions. So I encourage you, it really makes me happy, to be honest, when people sign up to receive weekly email messages containing the blog post of that week. So I invite you to go to my blog and sign up. You can peruse an annotated list of posts at this address. If you want to read post number 1, it talks about the purpose of the blog and what it's all about, by answering 10 questions about the blog. I'm sorry for talking for 5 minutes here about my blog, but I will point out it's a freely available thing. It's not a commercial product at all. And there's just a screen capture of roughly half of the posts. And there's another screen capture of roughly half. I do thank you very much for coming today. Take-home message, ask good questions. And you're certainly welcome to contact me by email with questions, comments, criticisms, concerns, anything you want. I think we have a few minutes here for questions. If Peter or Julie want to relay any of your questions to me. If you haven't typed in questions, feel free to type them into the chat window there.
Yeah, the only question we had during the talk was someone asked if you could share the data for the 1970 draft lottery, but someone else replied and found it on your blog already. So they've shared the link for that.
Great, thank you. Pretty much every example I use today appears in my blog somewhere. And I've already posted these slides under the presentations link at the blog. And the slides will be posted on the AMATIC webinar site within a week or two.
We did just get a question. It says, can you talk a bit about your assessment philosophy and approach?
Well, yeah, I mean, sometimes people ask me what constitutes a good question, and I actually try to avoid that question. I will write a blog post eventually with characteristics of good questions. My assessment philosophy, I give a lot of group quizzes. So when I teach a 2-hour time block, which I often do, I pretty much give one group quiz per class meeting. I think getting students to collaborate together is a great way to help them consolidate what they've learned and summarize their notes and help each other out. I give a lot of group quizzes as well as exams. The group quizzes are always open book and open notes. My exams are generally open book and open notes. I always try to have at least half of the points be on conceptual questions as opposed to calculation-focused questions. I actually aim more for 2/3 or 3/4 of the points to be on conceptual understanding as opposed to being able to do the calculations. Although I do ask students to do calculations as well. I hate to keep pointing to my blog, but I have a blog post with 20 multiple choice questions I like to use on final exams. I have another blog post with 4 multi-part open-ended questions I like to use on exams. I have a 2-part blog post with 13 5-part quizzes that I give to students. So I've tried to answer quickly and point you to some other things that show you how I go about assessing students.
We had more of a comment here. It says, your blog is fabulous. I've read it all, signed up for weekly emails, and will be using many of your wonderful ideas. I have a request for a future post on p-values of hypothesis testing and writing conclusion sentences. So there's one of your other ideas that might get you to a year.
Great, thanks very much.
Question, can you recommend any online simulation tools?
Sure, I should point out that the applet results I was showing you come from the tools that my friend and colleague Beth Chance developed. You can find those at rossmanchance.com/applets. So my last name, Rossman, that's last name, chance.com/applets. Those are freely available to anybody. There's also a collection of tools put together by Robin Locke and his family, who have written a textbook for introductory statistics. If you go to, is it lock5stat.com, I think, LOCK5stat.com. Their tools are called StatKey. I don't remember if it's statkey.com, but if you Google StatKey, one word, you'll find those tools as well. And commercially available packages are have good tools as well. The thing I like best about the tools that Beth Chance has developed is that they're very visual and very interactive. And there's lots of other good options there as well.
Okay. Do we have any other questions for Alan today? If you do, now's the chance to enter it in. While we're taking a few minutes to do that, let me wrap up some comments. Alan, I'm going to stop your sharing.
Sure.
And then share. Okay, go back to. Okay, so thank you everybody for participating in today's AMATIC webinar. If you're not a member of AMATIC and would like to, so you can get information about upcoming webinars, we encourage you to join. We do have a page on Facebook where you can keep up to date on all things AMATIC. We have national conferences coming up this November in Spokane, webinars and more webinars coming and traveling workshops. Once again, this will be posted within a few days, up to a week, to upload the recording. And then if Alan, if you would be willing to share the PowerPoint, we can upload that as well.
Absolutely.
And then we have the survey evaluation for the webinar. We have the QR code and the link, and I'll be putting the link in the chat room for ease. For those who are wanting to request a certificate of attendance, one of the questions in the evaluation is to make that request with your name and email address. So if we could, by way of a chat comment, if you want to thank Alan for participating, for Julie for helping coordinate this. And if there's any last minute questions, we'll be happy to take them. Okay.
I saw a question about what would I change or how would I tailor these ideas to classes of students who have lots of difficulties based on life circumstances or whatever. I don't know that the questions need to change much. You might do a lot with group work and have students help each other and have students work in groups during class, not just on the quizzes like I do, but also during the learning activity part of class, which I also have a lot of group work as well. So that's one thought. One thing I don't do much of myself is posting videos online to ask these kind of questions and talk students through how to think them through. That's a thought also.
Okay. Here's a long question. Are you able to see the chat now, Alan? Now that
I am, yes.
Okay. We got a question from Dana Feldman. Did you find that one?
Yeah, the one with the socio-emotional challenges
Okay.
and holes in their background knowledge. So yeah, that's what I was responding to when I said
I'm sorry.
work could help, maybe posting videos. I suspect that a lot of people listening to this know more about things like mindset and grit than I do, but I'm starting to learn a lot about mindset and grit, and I think those are important factors. And convincing students of the importance of mindset and the importance of collaboration and working together, things like that, I think can be very beneficial. I don't have clever ideas for how to achieve that, but lots of people who know a lot about it have written and spoken a lot about that.
I'm going to go ahead and stop the recording, but if there's any other last minute questions, we can see if